Surf's up, crazy physics lovers. Today we're going to be dealing with coalescing waves and knowing where they are. So we're going to try to find where objects or images are located in curved mirrors. So let's get started. We've got a fantastic problem here. So one of the example problems of this is we want to display a video, which is just images with sound. From a digital display onto a projection screen 10 meters away from a mirror whose focal length is 0.5 meters. Three questions we could ask of this are: what type of mirror can accomplish this, concave or convex? Where do we need to put this display to create a focused image? We gotta worry about that with curved mirrors. And what problems could arise from this method, and how could we fix them? Because sometimes they're very, very easy. So let's get a look into this. So let's take it part by part. So we got what type of mirror can do this? So if we go back to our notes, we can take a look and we can figure out which this is. So we know that concave mirrors can create either inverted real images or upright magnified virtual images, whereas convex mirrors can create only upright reduced virtual images. Now, if we want to project this onto a projection screen, that means that we want to have it in the real world, which means that we only want a real image. So that means that, of course, we have to choose the concave mirrors. So that would be the answer for part A. Quick, easy, to the point. Then for part B, where do we need to put this display to create a focused image? So the way that this works with concave mirrors is it creates a real image only when the object is beyond the focal point here. And you can see our focal point right here represented by F, and the center of curvature of the mirror represented by C. And this is our concave mirror. When we put in our ray diagram for this, we can see that it will coalesce into an image back behind the object. So this is something that we wanted, and we can figure that the object probably has to be in front of where the image is coalescing if we really want it that way. And there's a couple reasons for that, but let's get into the math of it because we want to find where does it show up. So we have an equation for the relationship of these values. 1 over dO plus 1 over di equals 1 over F. So this is where dO is the object distance, which is shown by the bracket here. So it's the distance between the object and the mirror. Di is the image distance, which is represented by the green bracket here, which shows how far away from the mirror the image shows up as a focused image. You can get an image almost anywhere, but it won't be focused except at a specific point. And F represents the focal length, which is shown by that black bracket right here, in which the focal length is inherent to the mirror. So if we put the object elsewhere on here, we could get a image distance somewhere else, but the focal distance will always remain the same unless you change the mirror. Special little note here, even though it's not relevant to this problem, but for future problems that you may face, if there are any virtual distances which are on the opposite side from the mirror of the object, or of the mirror from the object, so if we had any values over on this side, on the right-hand side, they would be virtual distances, and they are negative values when they get plugged into our equation here. But there aren't any, so it's, we don't have to worry about it, but it's still good to know. So we want to pick out some relevant information. We've got this, anytime that we mention a number, it's usually relevant, but we got to figure out what it means. So we have onto a projection screen 10 meters away. So if we're projecting it onto a projection screen, it is not the object, unless we're trying to get an image of the projection screen, but we're trying to get an image onto the projection screen. So that means that that is actually the image distance. The other value that we can quickly identify is that it even tells us right here the focal length is 0.5 meters. So that's what the F value is. So let's look back at our equation there. Now, once we have our equation, we can substitute in these values in their appropriate places. So now we have 1 over object distance plus 1 over 10 equals 1 over 0.5. A special little note, if you have different units here for the projection screen and the focal length distances, you have to put them in the same units. You have to convert. We won't deal with that often, but in case you ever see it, note to convert, everything has to be in the same units. Next would be to move every non-variable term to the other side. So the 1/10 here does not have a variable associated with it, so we want to move it to the other side so that we can solve for our variable. Then we want to find some way of bringing these together, because we cannot just straight do the subtraction. We cannot do 1 minus 1 on the top and 0.5 minus 10 on the bottom. That is not how fractions work. What we have to do is we have to find a common denominator. So the common denominator for here would be 10. So we multiply 0.5 by 20 in order to get to 10. We multiply the top by the same thing so that the fraction does not actually change. The value is not changed of the fraction, it's just its appearance. So we now have 20 over 10 minus 1 over 10, which we can now combine into 19 over 10. But be careful, this is not our stopping point, because we have this is 1 over the object distance. We need to solve for the object distance, not 1 over it. So we must, since this is the reciprocal, take the reciprocal of it and thus flip it to find what its value is. So we flip it, so now it's 10 over 19. This equates out to 0.526 roughly. This is not where we are done, however. It is not fully complete until we have interpreted and given our final answer. So if we interpret this correctly, this represents the object distance, and everything was measured in meters, so the answer would be the display should be about 0.526 meters in front of the mirror. Okay, we got a positive value out, so that means that is a positive distance. We should expect this with an object, but always trust your formula and see if it makes sense. We see that we got positive value out, which means it should be on the same side as the image, since we said that was positive, and indeed, according to our picture, it is. So, now that we've got that, that is the answer to B. Last problem is C, and I'm going to refer us for this problem. What is the problems that could arise from this method, and how could we fix it? This is more of a kind of think a little bit about what you're doing question. Let's go back to our diagram here. We can see here's our object, here's our little display screen. We can definitely project an image, but oh look, our image over here, it's upside down, it's inverted. So the only thing this creates a problem. Everything's going to be upside down and left side right. Anything that was supposed to be on the left side of the screen is now on the right, so making any text readable is going to be very, very hard. You can't just even do a screen flip, because that also would still leave you left side right. But what you can do, and there's a simple fix, that is rotate your object. So if you spin your display upside down, you are creating a upside down, left side right object, which when it gets inverted by the mirror will create a right side up and correct left and right side, so that everyone can watch your video and everything is all great. So I hope this has been informative, and if you need any further assistance, feel free to contact me, and I will see you next time in class or on YouTube.